Good afternoon. So, the first module of the design of RF front end, these two classes from now to up to 5 o'clock, we will mainly talk about the basic RF design, because for any functional modules or total systems, you need to know about the specifications, how to quantify your results, and how to qualitatively assess your design. So, you have to know about what are the different performance metrics, how they are interrelated, and from there how do you go into your design. Essentially, in any design in RF front end system, you will find that they are giving a system design, just couple of few specifications they will provide. But from that specification, it is a top down approach. You have to actually derive your system level specs to the each functional modular specs, and then back and forth, and finally go to the final your own specifications. So, with this view in mind, I have made these modules. So, let us first start with what is RF frequency, where we actually know and where are the interests of today's modern cell phone or telephony or portable communications. Our region of interest is basically 100 megahertz to 10 gigahertz, that is the RF band. Essentially, you are working if GSM or ISM phone is 935 to 950 megahertz, and Bluetooth and Zigbee is 2.4 gigahertz, and so on. Very recently, even people talk about 400 megahertz for W band, that is for biomedical instrumentations. There is a special band engaged to this, is 400 to 419 megahertz. And for video online streaming, the frequency band is around 427 to 600 megahertz. Now, there are two issues. One is the band, and second one number of channels. And this is the most critical junction we are. Basically, you know that cost of the channel and the bandwidth is very, very expensive. Therefore, all the design now lead to that minimum bandwidth, how to push more number of channels. So, your frequency tolerance are pretty high. So, you need to have a very stringent design. For example, you are designing a frequency synthesizer. If you design a simple frequency synthesizers which can cater to the need of a Zigbee, you need an integer n frequency synthesizers which can cover 76 channels, having a bandwidth of roughly 80 megahertz. But when you have say 100 megahertz or say 50 megahertz or 26 megahertz channel bandwidth, and you have to cope up with say 100 channels, then the neighboring channel frequency tolerance and to design a frequency synthesizer for that is extremely critical. Another issue is that any communication systems, you know that the information content is within the amplitude of the signals as well as its phase. If you look at A sin omega t plus phi, so A is the amplitude that contains the information, frequency is the carrier, and phi is the phase. Now, phase also contains the informations, and if there is any noise in the phase, that will also contribute to the distortion of your extracted signals. And even somehow, you might be losing the signal at all. Phase distortion is quite critical, because you know that if amplitude varies, if there is some disturbance, but you know that what is the maximum amplitude that can vary within the limits of the bias. But for the frequency, you know that it can go anywhere. you do not have any control of the frequency phase variations. So, phase noise performance of any systems, especially in a communication design, is very, very important. We will talk about each of this, like phase noise, linearity, the gain, and how it differs from the standard analog design one by one. So, we talked about the frequency range, which is from 100 megahertz to 10 gigahertz. When you talk about that, then few things immediately comes to your mind, that the lump parameter model will fail, and you will have to have some kind of a transmission line model, and there will be a transition from Kirchhoff's to Maxwell. Today in the morning I mentioned about this. And then the standard two-port model Z, Y or ABCD parameters may have some limitations in analyzing your circuits, and sometime you might have to use the S parameters as the RF and microwave design. So, with this, let me give any subjects when you study or any research, there must be some objective. And if you look at that, the RF front end having applications almost everywhere in today's generation, right from wireless communication to sensor to medical, radio astronomy, navigation, and so on. And each of them having their own set of specifications, but there are some design generic guidelines. So, we will try to give you a generic guidelines how to design any RF systems, and at the end we will look into some of the specifications, for example, how to design your own cell phone front end. So, that will be the kind of things which we will explore for the next 2-3 hours. Now, coming to this, the first thing in the morning which I have mentioned, that Kirchhoff's law based our main small signal AC analysis, where the Maxwell equations provide us the electromagnetic propagations and its RF and microwave implementations. But you know, these two fundamental laws, they do not fight each other philosophically. Let us try to understand these two, and then you will understand fully that what is the limitations of both the cases. If you look at this 4 equations, set of equations of Maxwell's, and if you look at the other hand side, if you took the curl of H equal to epsilon d dt plus j, this is a very standard, all of your students know this. Now, if you take the divergence of both the sides and you assume that this epsilon part is 0, question of taking epsilon 0 means what? If you look at the velocity of electromagnetic wave in free space, it is 1 by mu epsilon, and in the media it will be epsilon epsilon r. So, if the propagation of electromagnetic wave is very, very fast, it's close to infinity, then we can consider this epsilon is almost reaching towards 0. So, if it is the case, this epsilon goes towards 0 or mu goes, the permeability goes towards 0, then this part becomes 0. So, if you take divergence of curl of H and divergence of J, both the sides, and all of you know that divergence of curl of H is nothing but 0. So, your divergence of J is 0. What does it mean? It is nothing but your Kirchhoff's law. Okay? So, you can arrive into the conclusions of the Maxwell, from the Maxwell equations to the Kirchhoff's law. Fundamentally, you have assumed 2 important things. One is your epsilon tending towards infinity, that means the signals which is propagating to the media is very, very high speed, enormous speed. So, that causes epsilon to goes to 0. But if you look at the second case, you can make it as your homework. You can easily arrive into the Kirchhoff's voltage law. If you look at this divergence of curl of E, if you take the divergence of that, you can take the line integral of this. So, you can find this, the voltage or the field around the loop is also 0. So, that easily you are going to the Kirchhoff's voltage law. So, both are fundamental laws, they are not clashing each other. You have to look from that perspectives. What is that perspective is important when you go for an RFIC design. You are getting the signal from the antenna and then passing through some RF filters and finally fade to an LNA, which is your chip, the front end. Your dimensions of those components is important. If the dimension, if you look at the wavelength and the frequency characteristics, suppose this is the wavelength and your component size is small compared to that, then do you perceive any kind of a phase changes from this point to this point in the components? Answer is no. But whenever you have some kind of a wavelength or the frequency is very high and your component size is big, then you will find there is a change in the phase of your signals while it is propagating through that component of this. So, that introduces some sort of change in the phase. Now, our early days we know that we will actually introduce the change in phase. Resistance would not. Resistance, the voltage and current, they are in the same phase. But if there is a capacitance or there is an inductor, you will find there is a phase lag and a lead. That strikes the issue. That means, whenever in a component size is comparable, if not more, than the size of the wavelength for a particular frequency, then there will be change in the phase along the length of the components. So, the components has to be defined not by a simple discrete discrete lumped models like a resistance or capacitors, but it will be actually a transmission kind of models of RC or LC or RLC kind of a network will be required. So, that is where you know that a simple conductor becoming an LC network or a capacitors, which is essentially becomes an inductor connected with a series resistance and a capacitors parallel to a resistance. So, you have lot of this parasitic resistance become a combination of LCR circuits and so on. What does it mean? That means that your resistance or discrete components are not actually having only that resistance or capacitance or inductor values. They are actually combination of all this. Okay? What it actually means to your circuit design, this is called the parasitic aware design. That means, you will have lot of parasitics, okay, in and around the device and the components that will come into your system while you will be simulating or while you will be realizing at essentially at high frequency. Now, what is that frequency which is to be critical? I give a thumb rule for that, that whenever the size is 1/10 of the lambda, you just calculate mentally what is the frequency of operations, find out its wavelength at that media and then divide by 10. If that size is comparable to the component size, then actually your lump parameter model started to fail. Okay? So, you have to take care of this Maxwell equations or kind of a 3D electromagnetic or 2.5D electromagnetic solvers, or you have to get some kind of a transmission line models. And electronic circuits in RF front end not only have the MOS transistors, you will have the passive components too. So, immediately you recognize that RF design becoming a very complicated in that way, that one hand you have the Kirchhoff's law based these all design tools, On the other hand, the electromagnetic wave based Maxwell wave equations based EM solver, where to where use. You understand now both should be used for designing an RF circuits. If you look at the today's dimensions, for example, if at say 1 gigahertz, I say that suppose it is 1 gigahertz, then 30 centimeter in air. So roughly I say that it is in electromagnetic wave when propagating to the silicon, so make it 1/10 of that 3 centimeters. 1/10 of that is 3 millimeter. So 3 millimeter is the size, and what is your device dimensions? A full transceiver chip now can be designed. In fact, I have designed in 1 millimeter into 1 millimeter die. So 3 millimeter is the size where you have to go for this kind of a transmission line models. But you need not to go worried about when your dimensions, the footprint of our device is 110 micron, 1 micron, even nanoscale devices now at the moment, so you don't bother about. So that stands that whatever cadence, synopsis, or the Tanner tool at the moment you are using are applicable while designing these RF circuits, because none of your components are actually within the limits of that up to 10 gigahertz. It's not an issue. But in RF circuits, you need to have those passive components, right? You have inductor on chip, you have capacitors, you have transformers, you have interconnects. Those dimensions are not so small. They may have the dimensions close to 3 millimeters. So to design those, you have to get some kind of a solver, right? Like IE3D, or you can use some kind of HFSS or ADS kind of a software tools. So if you start your journey in RF design, starting from the antenna, then you know that when it goes up to the device, it is all electromagnetic solver. But when it goes inside the chip, it is all the KCL, KVL based, the standard EDA CAD tools. But when it comes out, again, if you want to say transmitter, if you want to transmit through an antenna through a bandpass filter or some kind of a polyphase filters, then on that design, you might have to use those solvers. So why it is so critical? Now you understand the design. Your transistors, those who are small signal models, have used GM-Pi models and so on. You are only concerned about the oxide cap and so on. But now you understand that when you have high frequency, then those MOS devices also having lot of parasitic capacitances. So those capacitances will also be incorporated in your design. And why the system is becoming so complicated, I am just explaining you the facts that why it takes your time because of this paradox. The paradox is that suppose this is a MOS device, right? And all of you know that it has got a capacitance called CGS. Okay? Now, I have a source, and that having a resistance of 500 ohm or 50 ohm, whatever, normally 50 ohm. And if you are to club this to this MOS device, what you see? This frequency is say 2.4 gigahertz. You want to connect it to that. Will it work? It will not work because you have a parasitic cap. So it will it will not go through your transistors, it will pass through the capacitors and going to the ground. So somehow you need a matching circuits to match the impedance as seen from the source side and also seen from the node of the device. They should have the conjugate at least, so that you can have the maximum power transformations. How to do that? Since it is a capacitor, then definitely you need some sort of an inductor and a resistance, something. Inductor having a resistance that will work on in that. It may be in series or it may be in parallel, whatever be you like it, you do it. So, this inductor resistance will be matched with the real part of that, or you can have a combination of resistance and inductor. Essentially, its role is to negate the capacitance and to offer an impedance of 50 ohm to match with the source. That is the main part, very simple. Now, it is very simple up to that, but what I have mentioned, an inductor is not an inductor. The inductor is also a capacitor. What I say that, if you look at the model of an inductor is like that. An inductor, and there is a resistance, obviously the coil would have a resistance, then there is a capacitor. This is called intercoil capacitance. Then there is another capacitance which is called the capacitance from the inductor to the substrate, and then the resistance and capacitor of the substrate, like that. I will explain it later in with diagram. So, this become your inductor, my God. So, there are 9 parameters are just there to define your inductor. Now, think of it, you are adding an RC RLC network just to terminate one resistance. Then you have to reduce or effect of capacitance, you need another inductor. That inductor will also introduce a capacity capacitance. That capacitance will also introduce some inductor. Oh my God, where is the end? So, you understand the paradox. So, that is called the design optimization is very critical in this case. So, that is why when you want to have your S11 minus 16 dB, you are elated after 3 months, because it is very, very difficult. You have to make your W by L in such a way that your GS, CGS values is within a reasonable limits, and then you make your inductor and capacitors values in such a way. You might achieve, but suddenly you find your inductor value is 12 nanohenry, and this is not at all possible to implement in the standard, say UMC or TSMC process, because they have given a guidelines that it is within, say, 2 to 3 nanohenry with a quality factor of 4 or 5. Then your hands are tied. Obviously, you make through your mathematical calculations to find out the value which is 10 nanohenry works fine, but you have no other options, you cannot implement. So, that issues are coming. Okay. So, that is why I say that if you can have a generic approach to design, you will be able to make a fantastic design at the end of the day. Let us try in the second case. All of you having a background of analog design, right? So, that is why this particular slide I made for them, because when I select the students, then the participants, then I found there will be at least 2 to 3 years of analog. So, I understand that in analog design, you are all experts. So, all of you know that suppose I want to design some set an analog amplifier. So, what you have concerned mostly, so small signal AC equivalent analysis, you talked about the linearity of an amplifier, right? You talked about the stability of the amplifier. You talked about the noise in few cases. Essentially, the noise will define the lower limits of the signals without corruptions. But if we look at the RF amplifier, the same thing, what additional things you have to look into, that is important for your case. So, in case of RF or microwave at high frequency, which is beyond 100 megahertz, there is no such thing in the matching, but you think that there is a matching an issue. Noise is extremely important in RF regions, various kinds of noise. So, I will talk about the noise model, how to model a device. Then the stability. You do not know your amplifier will be unstable at a particular gain. You might have a stable circuits, but some parasitic unwanted path in between can cause oscillations, and once the oscillation builds up, then you have no way but the amplifier becomes an oscillator. Then the sensitivity. When you have a receiver, then you know what is the minimum signals. For example, in your GSM-4, what is the dynamic range? It's 47 dBm to minus 112 dBm. So few nanowatts of power actually being received. And you are designing it, the front end. So you have to be careful what will be the gain of your amplifier. And if the gain of the amplifier is fixed, then you are at a problem. Why? Because for what input signal you will fix your gain. Suppose my signal strength is 47 dBm and my gain is say 30 dB, fine, good. But suppose the signal is minus 119 or minus 112 dBm, will that suffice? I need to increase my gain. Always you feel you have a no tower to full tower. So your amplifier in your cell phone should not be a fixed gain. So there will be variable gain, and that too should have a very, very low noise. Why? That will also explain. So you need the fast stage is also very critical. It should have a dynamic range to adapt to the strength of the signal as received, okay, just for your cell phone. And we will talk about the linearity is very important, because for an amplifier, when you design, then the signal strength when goes up, what is the maximum input signal strength it can actually handle? Otherwise, what will happen? It will go to the nonlinear region and introduce large number of harmonics in the systems. And that harmonics will finally distort, not only distorts, your fundamental amplitude will be go down, because energy conservations. Your energy is, suppose I want 2.4 gig output, and suddenly I found there are a lot of harmonics are there. So your fundamental components amplitude will go down, because energy is distributed to other harmonic components. Therefore, this is also important, that how would you handle the linearity of the systems. Now coming to this, the little bit of idea about the today's technology means whatever technology at the moment you are using, you know that discrete components being packaged. But if you look at this flow chart, I am not going to go talking about all this. Problem is the scaling and the cost. An RF on-chip design, first the development cost is pretty high, okay, because you know that you have to use those huge expensive tools. But once you have done it, then it will be throwaway cost. I remember that the first chip which I have developed for a multinational company is a 1 volt transceivers. The challenge given to me is make it low power so that one battery can stand up to 5 years. It's for sensor applications. And it will work at 1 volt with 1.8 volts process. So you have to scale down that one. So you understand. The chip process is 1.8 volt, but it should work at 1 volt. So design challenges this. And that too using a digital process, because I said that it will be used along with the digital circuits, low power digital circuits. So mind it, this kind of design, you cannot do it by choosing this millimeter or microwave, those kind of components, monolithic integrations. You have to change the whole thing. But here you can play with that. So you can, in the design, you can tweak it and make the design suitable for that scaling. For 1.8 volt design can be done to 1 volt, and the cost is pretty less and is very light. Even at 1 millimeter into 1 millimeter area is a big area in today's 65 nanometer technology, you can jolly well feed your whole transceivers into the systems. And power consumption is also pretty low. Even now people talk about transceivers, which can, we are all designing in the milliwatt power, but actual design, the next generation design will be sub-milliwatt design. That means it can be used with, say, few microwatt, 100 microwatt, 200 microwatt for a transceivers, so that at the end, this can be used by energy harvesting approach. That means you do not need a battery. Just by energy harvesting, you can turn on your transceivers. Now come to this is the transceivers front end design. Now since this course is made for the teachers, so what kind of knowledge base, what kind of interactions you require across the departments is very important. So what I said that if you look at the RF design, then you have to know from communication theory, random signal statistics, transceiver architectures, IC design, CAD tool, wireless standards, then what various access scheme and so on, signal propagations that I have already mentioned. So you need to have an RF design. It's a combinations of flavors of each. That's why it's a very, very interdisciplinary nature. You have to know the communication standards. You have to know the signal statistics. You have to know the power, how the power is fed to the systems, and so on. And if you look at the design complexity, it is also very puzzling, because you find that all these parameters used for this design, for example, noise, linearity, gain, they are not actually independent parameters. If you tweak the linearity, immediately you say your gain will change, or if you reduce the power supply, then your phase noise will go down. Therefore, there is no such unique design rules exist in RF design, that I want this power supply, the W by L and R and C will be like that. That is a layman's things. It will not applicable here. You have to always tune the circuits to make it optimum. Okay? So an optimum design is important in this case, where every time you have to make iterations, including the W by L ratios of your transistors, including the passive components, with a very conscious approach how to negate their parasitics. Even the inductor can be used, can be replaced with a bond wire. I will show that. Even the interconnects can be used as a transmission lines. You do not know that sometimes the interconnects at a particular frequency acts as a particular kind of a transmission line, which can be used as a tank circuit for an oscillators. So you have to be innovative in that way. That's why microwave knowledge, your device fabrication knowledge, or the physics should be clear to you. This is, that whole transceiver chip, where these inductor chips are there, the capacitance block, and so on, all the frequency synthesizers. So we will show you the design of each block for the next couple of days. Now come to the next one, which is a summary of the observations. This is for you, that you go through each line and say that whether you have understood the basics of RF design. Let me go through it. First, I talked about the phase shift of the signal, which is significant over the extent of the component because its size is comparable with the wavelength. You understand what does it mean. When you go for high frequency, wavelength is going down and the size of the components is comparable to that. There is a phase change would occur and your lump parameter model will fail. You have to use. Next one is the reactance of the circuit must be accounted for, particularly those associated with the parasitic of the active devices. You understand that your MOS device, there is a capacitance CGS, there is a capacitance CDS, drain to source capacitance, gate to source capacitance, C to bulk capacitance. So all those capacitance will come into just for tuning or just matching one resistance with that. So it should be extremely critical to design this parasitic aware design. Third point, circuit losses cause a degradation of Q, reduction of frequency selectivity and noise performance. Very, very important. I will talk most of the time about the Q. All the component, now it is one design idea came up, is called Q-driven design. Because you know that in RF CMOS design, the main problem is the limitations of the on-chip inductor's quality factor, which is always not at all satisfied to the requirement limits. Only 3 to 4, whereas you require thousands or even hundreds, even 100. So you understand that you have very low quality components which is be used for your CMOS circuits, because the process itself is that having the limitation. including say 180 nanometer you can achieve 3 to 4 quality factor, whereas in 65 at 2.4 you can achieve 9 to 10, but you cannot go to 100 or 1000 or 1200, impossible. So that's why quality factor, which determines the loss factors, we'll mention that quality factor is actually tells a lot of things like the phase noise, power consumptions, the gain, what not. So if the quality factor is less, then you know that you are bound to compromise with your performance. Fourth one, noise especially arising from the circuit can be significant and its effect need to be modeled. The noise which you have not that way conscious in your analog or low frequency design, here the noise is very, very important. Why I mentioned that here the noise is not only your amplitude distortion, but also phase gets affected. If the phase gets affected, then your information is completely lost, because you have internal mechanism to control the amplitude distortions, but you do not have any mechanism to control the phase distortions. Therefore, when the phase is corrupted, you are gone. Therefore, the noise incorporations in the circuits, especially the phase noise, 1 by F noise, the thermal noise, I will go into that. That is becoming very, very important while you are designing your circuits. Fifth, the electromagnetic radiation, the capacitive coupling and the substrate coupling significantly after performance alter the performance of the circuits. We have not actually bothered about when you design something in analog design, that where my components will be placed, how it will be placed like that. But here, if you have wrongly placed your power amplifier within the circuits of an oscillators, then I will tell immediately your oscillator will start to oscillate at a frequency with the power amplifier, not with your local oscillator frequency, because all of you know that frequency pull up. So the dominating mode will start oscillating, and your power amplifier is a big boss, so he will actually punch your oscillators, which will actually turn on your frequency synthesizer. So everything is haywire, because you have just placed wrongly the power amplifier close to the VCO sides or frequency synthesizers. So power amplifier design, if you look at any commercial circuits, are always at the corner, or if possible another chip. Even the TI fast transceiver chip, the power amplifier is set outside the transceiver chip. Reflection issues, because circuit size is of order of wavelength that I mentioned, that when the components which are passives are comparable to that, then there will be, reflection means what parameters I am mentioning is your S parameter, S11 and S22, which you are considering for an analog design only the gain and the linearity. You talked about how the matching is made in the input side and output side. No, S parameters are not there, but here S11 and S22 are one of the important parameters essentially there. Nonlinearity causes distortion and unwanted frequency component. This is a very critical lines. You know, an amplifier design nonlinearity is not desirable, but sometimes nonlinearity is desirable. When I design a mixer, in a mixer you have the two signals, local oscillator and the RF in that goes, and one of them is actually acts as a switch, and other one which is a large signal, and other one is acts as modulating the transconductance. That is the current. So your RF in actually modulates the transconductance of the transistors, and another transistor is connected in series with that, which is acting as a switch. So that switching and the modulation that finally gives you the multiplication of the two signals. So essentially you are actually giving a nonlinear circuits. So in oscillators, mixers, you are using the nonlinearity of the systems. So that's why I say that if these 8 points are very clear to you, then actually you are one step forward in taking the challenges of RF circuits. Okay? It's okay up to this? If you have any questions, ask me. In RF, these basic concepts, if you have any confusions, you just tell me. So now come to the actual topic. The most important topic is the noise. Let's start with that. What kind of noises are there in RF circuits, which will be prevalent or which will be dominating case to case, which we'll talk about that. But let us try to have the noise and then find out that how to design, suppose I design an LNA, how this noise will be calculated for an LNA design. Thermal noise. The carriers are moving in all possible direction, Brownian motions, but essentially under an electric field, they are actually trained to move in a particular directions. And you have a kind of noise which is called 4kTr delta f, or the bandwidth. So that is the noise you have. If you look at that, you can model the noise, mind it, you can model the noise in two ways. One, when it is convenient to you, you can model the noise as a voltage source. Vn tilde bar, that is called average, it is called average voltage, and is the square, average of the square of the noise voltage, which is 4kTr delta f. Or you can go to a current model. Whenever it is suitable, you can make in that model. So whenever it is the voltage, it is 4kTr delta f, and whenever it is in current, the same noise expressed in that way is 4kT delta f by R. Okay? The same resistance provides the thermal noise. Now that becomes 4kTg delta f. Okay? So where K is a Boltzmann constant, T is the temperature in Kelvin, and G is the conductance, and delta f is the bandwidth. So we all of you know this, but now we will translate it into the MOSFET. Suppose you have a MOS device, how to calculate its thermal noise? Then it is pretty easy. We know that 4kT term will come, and that is gamma, one term gamma and GD0 is coming. This is the conductance. Okay? So this conductance is replaced with the conductance of the source to drain region conductance, and at 0 means at VDS equal to 0. So that is the conductance, and gamma is a factor. You know that this factor is baffling always in your design. What you will give gamma value? Textbook will give you some value, your literature will give you some value. So you do not know actually, you do not know actually that what value, but I can give you some guidelines. For a long channel device, gamma you can take it as 1, and for saturations, say for short channel devices, you can take 2 to 3, okay? And for long channel, when it is saturation, that is 2 by 3. But more important, audio devices are deep submicron technology. So for short channel transistors, you can take it as 2 to 3. Essentially, is more than 1. What is the logic behind it? Logic behind it is that if you look at the Brownian motion of the carriers in the conductor. So now here in the MOS device, the conductor is the channel. So now if it is long channel, then you can have a standard resistive model. So 4kTg delta f will work. But in case of when you are squeezing the size, your source to drain length is going down. So what is happening? Your source to drain length is squeezed, therefore what is happening? In the same voltage you will have the short channel effects, and short channel effect will introduce the hot carriers, and that the thermal noise will be more in that way. So we are expecting the gamma value will be high in a short channel device, but it should be done by trial and error or empirically, and better is to make transistors and then you measure it and find out the value of this gamma. But to safe design, you can take it as 2 or 2.5 for this. So thermal noise can be modeled for a particular noise is 4kT gamma GD0, and where the gamma values varies from 2 to 3. So that is the thermal noise. Next one is the gate induced noise. This is the most important noise which we always try to neglect, but that is a very, very important effects. Those who are designing the LNA, or especially those who are designing RF circuits, the gate induced noise is very, very important. Why? Because look at the channels. Suppose the carrier which is in the oxide to semiconductor interface regions. So these charges are actually being fluctuated. So you have suppose two plates, okay, like a capacitor, and one of the plate side, the charge is actually fluctuating. That is, they have a time perturbations. What will happen? Then there is a Q, at Q having a time perturbation, so dq dt. So that will introduce some kind of a current. So you understand that this kind of charge fluctuations within the oxide, one side of the oxide is semiconductor oxide junction, other is the gate junction. That is the capacitor I am talking about. So there will be some kind of a noise because of that fluctuation of charge, which will be transmitted to the gate, yes or no? So that is called the gate induced noise. And this, to model this gate induced noise is extremely difficult sometime, and most of the earlier design are not taking care of this design. Why I am saying it is important? When I first started my designing LNA, you know that LNA design you need to have a typically noise figure is 2 dB less than equal to 2 dB. And by 180 nanometer standard EMC or TSMC process, we have achieved 1.5 dB. So we are related. 1.5 dB LNA at 2.4 gigahertz is fantastic. Unfortunately, we found that another model we have used, we are comparing the same design, we translate into another PDK file. Where this gate induced noise is incorporated in that model, we found that the noise, same configuration, same W by L, the noise figure becomes 2.2. So 0.7 dB noise figure just changes because this model is inaccurate. The gate induced noise is not taken into account. So what I am suggesting you that you look at it, if the gate induced model is available is fine, otherwise you can estimate this by this formula, that is 4kT delta Rg delta F, where Rg equal to 1 by 5 Gd0. Gd0 is the source to drain conductance at 0 VDS. So you calculate Rg, and then 4kT is known for a particular temperature, delta F is your bandwidth, okay. Say for GSM it is 26 megahertz, for Zigbee it is 78 megahertz and so on. And then delta is a factor, and that factor till now, this is a very, very funny things. For long channel we got 4 by 3, but for a short channel it is say the 2 times or 3 times like that. So it is 4 to 6. So you understand the challenge of this, the accurate model. So better you make your own MOS device and test it and find out, and those are experienced, they know what values they will take. So I give you a range of values 4 to 6 depending upon process to process into that. So you can estimate that gate induced noise, okay. What I am saying that better is you calculate the noise and then introduce an additional resistance in series with the gate, whose thermal noise is equivalent to the gate induced noise. What I am saying that suppose you have this MOS device, you calculate that gate induced noise, okay, which is equal to your 4 gate induced noise, which is equal to your 4kT delta Rg into delta F, and then you just add one resistance to that, okay, say Rx, whose equivalent 4kT Rx delta F is equivalent to this, is possible. Then you put it in your simulation model. Am I clear? So it will, as if it will take the gate induced noise as the thermal noise of the additional resistance connected with the gate. Then your model will be more accurate. Your simulation, you know that now the challenge is that whatever post-layout simulation you have done, your silicon should be within 1%. And nowadays TSMC 65 nanometer, we found that even with 1% you will get the value. Whatever value you have predicted, the simulations after post-layout is more or less is mimicked into the silicon. So your model should be accurate. So I am giving you one of these idea from my experience that how you can actually model the gate induced noise. The next one is the short noise. Now the short noise is a very interesting thing. Whenever it related to your bias, short noise doesn't depend upon your AC current or voltage. It is not the small signal. Whenever any charge or DC current passes through the any kind of a potential barrier, that introduces the noise, okay? And that is In squared, there is the average noise square of the noise current is twice Q I DC delta F. So that is essentially coming from the your biasing circuits, right? When the DC, your bias current flows, like quiescent conditions you are defining, then those noise are important. Next, the most important noise parameters is called the 1 by F noise or flicker noise. This 1 by F noise, you know that if you look at the characteristics of any noise of any MOS device, then it is like that. It will be like following, and then it is going in this. And this noise is called the thermal noise. This is the thermal noise period. And this is the frequency, okay? And this is the center frequency. Suppose this is 2.4 gigahertz. So within 2.4 gigahertz, if you just make say 1 kilohertz, 10 kilohertz, 100 kilohertz, or 1 megahertz, 3 megahertz, 100 megahertz, depending upon what is the offset, then your noise phi will actually is very high at this, and then at the center frequency or neighborhood of the center frequency, and then when you go down with increasing frequency, suppose 3 megahertz, 10 megahertz or 100 megahertz offsets, then it is called 1 by F noise. So the noise contribution is less. So it has to be very careful that suppose you are designing an RF front end circuits up to LNA, you know there is no frequency translations. If I just draw a transceivers, it will be clear to you at this moment. Suppose this is your antenna and this is your RF filter, and then it is LNA, and then it is mixer. So what I am saying that if it is the frequency is 2.4 gigahertz, frequency here is also 2.4 gigahertz. Now you have a local oscillator, then the frequency, this is omega C and this is omega LO. So what will be the frequency? It will be omega C minus omega LO or omega C plus omega LO. Now this omega C omega LO is a lower frequency. So what does it mean? The noise, if you look at the thermal noise, that is fine. The thermal noise contributed by each of the components is good. But point comes here, up to that there is no change in the frequency. But here the change in frequency occurs. It is going to lower frequency omega C minus omega LO. So here if you look at next step, you are incorporating what? 1 by F noise. If you side by side going into that, what you are seeing? That you cannot neglect the whatever you have neglected here, because this region is up to say 2 gigahertz. So if you design up to 2 gigahertz, after that you might neglect the 1 by F noise, because this is more or less equal to the thermal noise. But beyond the 2 gigahertz, it is going like that way. So now you say it is always less than that, because it is down converted. So here your 1 by F noise becoming important. Clear? So in a circuit or in the total systems, when you design, you have to be careful that what is the frequency and what are the noises will be dominating to estimate the overall noise of the system. So this is the noise issue in nutshell about any RF circuits. Next one is the noise figure. So if you look at the noise figure, let's go into this is a standard definitions of noise figure. That is the total output noise power divided by, first of all, noise figure and noise factor. Always it is misnomer that noise factor will give it to noise figure. Actually, first you define the noise factor and then you make these 10 log 10 definitions to make it to noise figure. So, you will find that the total output noise power divided by output noise due to the input source, that is your noise figure. But one of the important thing is this, the noise factor and what will be the maximum value of noise factor. So, if a system has no noise, there is no system, no noise is incorporated here. So, you will have the noise factor 1. Okay. For example, this is a very interesting case here occur. If input signal contains no noise, then SNR in equal to 0, and then SNR in becoming infinite because your no input signal noise. If it is infinite, then your noise factor becoming infinite. What does it mean? Is it really possible? Actually, while defining for any RF system, first of all, you have to understand what is noise within the system and what is noise which is being fed to the system. Your system might have less noise, you can claim that one somehow, but your input after the antenna, you cannot say your system does not have any noise, because radiation resistance of an antenna having the noise. So, how can you say that your input noise is 0, that is why SNR in is infinite. So, that kind of expressions mathematically is given, but practically it has no meaning. So, SNR infinite in infinite, low noise input is 0 is not there, because your LED is connected with your antenna, and antenna have a radiation resistance that gives the noise. So, noise is important. Second is important, where you find the most, there is another, I would say, thinking process starts here. I start with a simple example, then you understand the intricacy of that. Okay? Suppose you have suppose this is my antenna, right, giving a 50 ohm resistance, and this is the source connected with a simple resistive load RP, fine. Then what will be the condition for which I will get the maximum power transfer, and what will be the conditions for which my noise factor will be very small. Maximum, minimum is 1. Okay? So, let us try to figure out. Then you understand in RF design where lies the problem. Now, all of you know that the noise factor is input Vn square by A square. A is the, that Rp Rs divided by Rs plus Rp. So, you can find out the corresponding noise factor is 1 plus Rs by Rp. So, you can just make some manipulation, algebraic manipulations to find out the noise factor of these systems. But important point is here, how to make the noise factor minimum here? You tell me. Your Rp should be, because Rs is fixed given by the antenna, which is 50 ohm. Only option is that you have to increase Rp to infinite. If you make Rp infinite, then what will happen? Is it possible for you to have the maximum power transfer? So, both the noise and the gain cannot be done together. You cannot reduce the noise to the bottom, minimize it and maximize the gain. That is becoming a very trivial case in this case. So, what you can do it? You can optimize the design. So, that is why this curve shows that actually you can find out an optimum resistance for which both the noise and this maximum power, that means gain, is becoming a reasonable value, which is meeting your desired specifications. So, clear? So, that is the approach. There is no unique solutions or mathematical expression to design any RF circuits. You have to tune it, and then you have to find out what is the conditions which give you the best possible results. Okay? Clear this picture? So, RS and RP. Now, next one I will give you that I have gone into the component level, that is, this is the component noise, this is the linearity and so on. I will talk about that. But whenever you have a transmitters or receiver, it is a combinations of various functional blocks. So, I talked that your vendor or the customer will ask for specifications to be reached, which is few, 1 or 2. They will say this is the total noise figure, say 6 dB. They will say overall gain will be 37 dB and so on. But you are here to judge what will be the distribution of all these specifications among all these internal components and the functional blocks. So, step by step we will learn this. But we have to have some mathematical formula for that. Suppose this is the antenna with a resistance Rs, and that is having a thermal source V square Rs, and that is a noise contributed by this stage. So, these two stages, they are matched. Then noise figure of the overall systems, this is your very known thing, is that noise figure of the system is noise figure is the first one, and noise figure of the second one minus 1 divided by the gain. And if you look to the nth side, then it will be noise figure of the mth side minus 1 divided by the product, or the in decibel, it is the addition of all the gains of the previous states. But what is the catch into this? What we understand from there? That is, I have LNA, after that a mixer and so on, filters, so on. Now, if you look at this one, the noise figure, the first stage noise figure is unaffected. Whatever be the noise contributed by the stage 1 is actually becoming the main contributing factor to define the overall noise figure. Suppose my GSM phone, which is normally 6 to 7 dB noise figure. So, you understand that the first LNA, what kind of noise figure I should have? It should be much less than 6 dB. That is why you are going to have a specification of less than 2 dB or close to 3 dB. And then rest of the things, for example, mixer. The mixer might have a noise figure of 12 dB, do not worry about it. Why? Because mixer noise, suppose it is 12 dB, actually it is divided by the gain of the amplifier. So, contribution of that noise from the mixer is basically is reduced because of the gain of the previous stage. Clear? So, that is why a low noise amplifier, that means you have a very low noise close to 2 to 3 dB, less than that, and also a huge gain. How much gain? Huge means how? It should be around 16 dB. And what is the S parameter? What is the gain? Is S21. So, S21 of an amplifier, low noise amplifier, the gain should be around 16 dB or above, and the noise figure should be around 2 to 3 dB, if not better than that, including the gate induced noise. Because the gate induced noise, if you do not incorporate, it is an incomplete design, and that lead to your ultimately silicon results. You may not get the desired performance of your front end. Clear? That is why the LNA is so critical in this way. Another point, LNA and the antenna, what is in between? LNA and the antenna, in between you have a filter, because I have a bandwidth of 935 megahertz to 900, say 50 or something. So, in between I have to catch that signals, right? That is called RF filters. The filter is not introduce the gain, filter is always a lossy circuits. So, if you have a lossy circuits before the LNA, what it will contribute to that? Antenna seeing a filter, and filter having two purpose. One is band selection, second one is the impedance matching, because antenna impedance should be matched with your LNA impedance. Normally, LNA input impedance will be around 200 to 500 ohms, whereas your folded antenna would have 75 ohms or something like that. Then 75 ohms and 300 ohms you need to match. So you need a pi or t type filters. And that filter, normally with a 26 megahertz bandwidth with 40 dB roll off, it normally is a 7th order inverse Chebyshev filters. So that kind of a filter which have attenuation or the loss. So if you calculate that loss, suppose there is a loss factor is L, then while calculating the overall system noise figure, there is a beautiful derivations that has been given over here, you can follow it, that loss you simply add to the noise figure of the LNA. Clear? So when you have, say, my filter having a loss of minus 2.5 dB, okay, and then you simply add this 2.5 dB to the desired one. That means you have, say, 1.5 to 2.5 dB noise figure of the LNA, then overall noise figure if your stage 1 before the mixer will be 5 dB. Simple, because it can be proved pretty easily from these expressions that if you look at the loss in dB is available source power divided by the available output power, and if you look at the available output power means what? Why this fourth term is coming? Because you know that when the Rs equal to RL, then you have the maximum power transformations. If you have resistive load, then maximum is Vs by 2, okay? Then power is Vss square by 4. So that's why this Vin square by 4 term is coming, and then it is divided by Rs because that is the power V square by R, and then it is the, suppose this is the filter, this is the filter actually, okay, and this is the antenna, and then output is fed to the load, okay. I am talking about this part, and that contributes to the loss. So if you can calculate what is the loss, it is the Vin square by 4 Rs divided by Vth square by 4 R out, and which is like this. I am not going into the all this, you can do it, just it's very simple to calculate, and then you can find out that the noise factor of this filter is nothing but, it is the noise factor is L or inverse of G, that is the gain inverse, and if you calculate the overall noise figure in dB, which includes the filter and the LNA, both are matched, the source is matched, mind it, matching is very important, that is source is matched and your load is matched, then noise figure of the total is nothing but the sum of the loss plus the noise figure of the LNA in dB. So that formula don't forget, we will use this formula. Clear? So you understand I am starting from the antenna. After antenna, I have come with the filter, then going to the LNA. Okay, then we will design those. Now coming to the, when you talk about the LNA, you talk about the MOS transistors. Then how to estimate the noise of a MOS structure? What is this? Simple common source. Let's start with. So you have this Rs connected, and this is the capacitance to block the DC, and this is your MOS device, and this is the RD or the load. Then if you look at here, Rs, you just remove the input source. Okay, I am just going to the noise model of a transistors. Then what is happening? This will be replaced with the average square voltage of this resistance Rs. So I am talking about Vn square Rs. This is the noise contributed by the resistance. Clear? I am not considering the capacitance noise. Capacitance noise is Kt by C, but I am not considering. I am say ideal cap. After that I am coming. So noise is here. You find it? Clear. Next is the MOS device. What you have found in the MOS device? There is a resistance Rd. There you have to introduce some noise, thermal noise. That thermal noise, then you come, you take the voltage or the current. What is the output of any small signal AC analysis? GM pi is the current, I out. So I am taking here the current model of the noise. So I in square Rd. Then look at here, this is a channel, MOS device, the channel. So that will have a thermal noise that we have calculated 4 kT gamma GD0. So, that will introduce another current which is the FET noise. So, all these noise components I have placed. Okay. So, just simple transistors with a load and a source, we are having all the contribution of the noise, and we are not considering any other noise other than the thermal noise here. I have not considered the gate induced noise. So, how now you can add the gate induced noise? You simply add one a 4 kT here, you can add one 4 kT RG delta F. I am not considering this at the moment. Now, all of you know that what is the voltage noise, thermal noise is 4 kT RS delta F, then 4 kT gamma GD0 delta F, okay, that is the noise contributed by the MOS transistors, and this one is basically 4 kT, you remember, divided by RD into delta F, that is the noise contributed by the resistance. Now, all this now has to be transformed to the output, because I have to find out the noise figure. So, what is the noise input and what is the noise output? So, I have to calculate that one. So, how to calculate? Now, all of you know that whatever be here the voltage here VGS will act here the current as GM into VGS. Okay. So, we will go into that. The noise contributed here, the source, will be transconductance GM square into Vn square. So, whatever thermal noise is acting as a current noise here at the output, which is Gm square 4 kT R delta F. So, now all are transformed to the output. Okay. So, I have got the thermal noise contributed by the source resistance Rs, the thermal noise contributed by the drain resistance, and the thermal noise contributed by the MOS transistors, and all are now has to be added, superpositions. So, once you add that one, you have got the expressions Rs, then GD0 is the transistor noise and the resistive noise Rd, which is in the biasing. Then what is the noise factor? It is the output divided by input. So, what is your input? This is 4 kT Rs Gm square. So, you just divide this one, okay, and then you will find that the noise factor becomes 1 plus gamma GD0 Gm square Rs. Just to divide this factor Gm square 4 kT Rs delta F, you will arrive into these expressions. Okay. So, you find this, the noise factor is 1 plus gamma GD0 Gm square Rs plus 1 by G square Rs into Rd. So, this is an expressions which is an ideal expressions, because I will never have any source which will be connected to my device without any matching transistor, matching load. So, I need a capacitor or inductor. So, this particular expression is of no use actually for designing an LNA. What I said that you need actually some kind of a matching terminate. So, suppose I have introduced some inductor which will negate this CGS. Then you have to calculate, incorporate this L, that is your home task, that suppose this is VIN, then you just very simple, whatever you have calculated to be VGS will be divided. This is acting as a potential divider. So, what you say that you will make in this way calculations, that is suppose you have this Vs, okay, and that is a series resistance Rs. Okay, and then you have an inductor, and this is ground, and then it is fed to your transistors, right. What I say that because you have to negate that reactive components. So, now if it is this, then whatever voltage is appearing across the CGS, that is your V pi, will be Vs divided by Rs plus j omega L, right. So, that is your new VGS. So, now you use the same formula in spite of Vs Gm into Vns square, you are use this one, and that Vs is nothing but 4 kT Rs. So, you can use that source noise is nothing but this is replaced with the noise Vn square average equal to 4 kT R delta F. So, you place that value and then you will arrive into the expressions this one, that is the noise factor becomes 1 plus R by omega L plus 1 whole square. Just this one, you just look at these two expressions, there is a term R by omega L. What is R by omega L? Is nothing but 1 by Q. So, whatever be the gamma GD0 term, it is multiplied with 1 plus 1 by Q square. Okay? So, 1 Q factor is coming over here. That is why I say that why Q is coming so important. So, I am rewriting the expression, then you will be understanding why Q factor is so important. What I say that this is my noise factor. Okay? The noise factor is 1 plus R by omega L whole square plus 1, then it is gamma GD0, that is your intrinsic parameters, no problem inside. Then it is Gm square Rs plus 1 plus R, I am writing the same one, square divided by Gm square Rs Rd, right. This is the expression. Now, what I say that R by omega L is what? 1 by Q. That means the noise figure or noise factor, if it is in 10 dB, you multiply it with dB scale, 1 plus 1 by Q square into gamma GD0 divided by Gm square into Rs plus 1 plus 1 by Q square divided by Gm square Rs into Rd. So, you understand that your noise figure or noise factor, if it is expressed in factors number, then is becoming a function of this Q. Okay. So, what you try to take, you always try to have the if Q is less, okay, Q is less, then actually your noise figure or noise factor will bound to go up. If Q is infinite, you can neglect this term. Then you are almost reaching this value, which is the ideal case value. Clear? So, that is why infinite Q means larger the Q, you are better off. Clear? So, that is why you need a very high Q circuits or high Q inductors, but unfortunately you cannot do that. Why? Because in a CMOS on chip inductor, you cannot achieve more than 3 to 4. So, you have limited with the quality factors, right. So, this shows the problems of quality factor. We will talk about more while we will be going for the phase noise, because in the phase noise Q is very, very important. So, one important observations we found that the phase, that is the noise, suppose this noise factor is proportional to 1 by Q square. So, now you understand why this Q square coming into this. Now, coming into the next one, it is called the linearity. The linearity and a nonlinear system is pretty subjective and very mind intriguing. It is not so easy. Superposition principle, okay, you talk about memoryless circuits, okay, but actually very difficult to distinguish in a linear and a nonlinear circuits in that way. I am just hinting upon the paradox. The paradox is that first we define what is a linear system. That is, output can be expressed as a linear combination of inputs, everybody knows, and otherwise non-zero. And non-zero initial conditions, same RC circuit can be non-linear, its capacitance is charged, right, pre-charged. And time invariant means that shift in the input, any time shift in the input results and show the same shift in the output. So, like xt minus tau equal to yt minus tau. So, that is all, and if you know at a balanced differential architecture, then you know that your even symmetry will be vanish. So, only the odd symmetry, odd harmonics will come, so on and so on. But when you look at the linear time invariant and variant systems, suppose I am giving a simple system. There are two sources, VIN2 and VIN1. Okay. This VIN2 is an input signal, so that is equal to A1 cos omega 1 t. Okay. A2 cos omega 2 t, and this is one is A1 cos omega 1 t. These are two signals, right? And this signal VI1 is connected to a switch, and this is the load resistance R1. I am taking the output across it. Now, how we look the circuits? Okay, this is the intriguing things. I have blackened this part. So, you are talking with this system. This is now becoming a system, and that is your signal. That is the configuration B. That is this V in 1 is now we are looking from the signals V in 1 to V out, and this one as it is remains as V in 2 as A2 cos omega 2 t. And in this case, this signal, the second one or the VIN1 is coming to the system itself in the definition of the system. What do you mean by the black shade? Black shade means the system. Which system I am defining? Okay. When I am shading the V in 2 and the switch and the resistance, that means this becomes a system. V in 1 become outside the system. Clear? In the second or the C, I will find that I said the V in 2 is now outside the systems, only the system is V in 1 like that. Then in this case B, you will find that V in 2, this B, system B is a nonlinear system. Why? Because suppose the here you are changing its switch, suppose it is greater than 1, which is positive, then the switch is on, and if it is negative, then the switch is off. That is, it is switching on and off. So, some external factors, this one is actually coming into that, and it is switching your input signal. V1 is present, is there. So, A sin omega t is now switched at a frequency which is externally controlled. So, since VIN2 is a function of time, though that should be a time invariant one, that is true, but because the system clock VIN is a clock outside, say, it is outside the system, then it becomes this particular system is becoming a nonlinear time varying system. So, system B is a nonlinear time varying system, whereas here you know that the switch is within the system. You are only looking at the switch and the load. So, whenever switch is on, I am getting the output. When the switch is off, I am not getting the output. It is a linear system. But since VIN2 is there exists, so there is a time varying one. So, I understand to capture this one in your understanding, it is not so easy, because this is a simple examples. Actually looking into the circuits and which one is linear time varying is very difficult sometimes, because all of your designers looking at I am giving an examples, it is still a problem. An inverter which is charging a capacitors, fine. Inverter is charging a capacitors. An inverter in digital cases having two levels, 0 and 1. So, 0 means 0 volt and 1 means say 5 volt, 1.8 volt and so on. Now, it is charging a capacitors. That capacitors having some value, say 1 picofarad, 10 picofarad. Then all of we know that I have to calculate the overall energy or the propagation delay, which is a function of the load cap and the wire cap, the node cap and so on. These capacitance are all the MOS cap, yes or no? We are using the MOS cap. Which capacitance I will take? Since it is a MOS cap, it is a function of the voltage. So, 0 and 1 is 1.8 volt and other is a 0 volt. So, my MOS capacitors will change, yes or no? It will change. Then which capacitors I will take? So, it is becoming it is not an LTI. I am saying that it is a nonlinear, a linear time invariant. It is not that, it is voltage is changing, so capacitance is changing. Therefore, it is not a linear time invariant one. So, which capacitance will look at this? All these simulators, they are using some techniques. What the techniques they use? Because CV is a function of voltage, that they find. But what they say that CV is a function of voltage, that is fine. So, let us take the average value of this VLO to VH divided by VH minus VLO, that is becoming a CLTI. Clear? So, that capacitance are actually taken into that. So, sometime the linear among nonlinear, time varying and invariant, depending upon how you perceive the circuits, whether the clock is external or not external. Okay? So, that is way how the linearity things are coming. So, I am just giving this example to raise some thinking process in you, so that you yourself later on finding more and more examples to find out which are linear and nonlinear systems. But this is not our cup of tea at the moment, but cup of tea is the next slide, which is very, very important. Why it is important? Because all my devices are not linear, they have a nonlinear characteristics. I am always truncating the second order and the third order. I am happy with the first order. So, suppose I have a function y as a function of xt. Now, in a linear system, I know that yt will be alpha on xt, but it is a nonlinear one, then it will be alpha 2 x squared t and x alpha 3 x cube and so on, dot dot dot. And if xt is a sinusoidal a cos omega t, then while this signal is passing through a nonlinear, this is the transfer function response, then what does it mean? That in spite of the fundamentals omega t, I am actually getting 2 omega 3, 3 omega t and so on. So, all those harmonics are being produced while a simple pure sinusoidal mono frequency is fed to a nonlinear system, introduces harmonics. That is very important, because my signals which is coming in the RF, okay, and that is passing to the nonlinear devices will introduce all those harmonics like an oscillators, then I am gone. All these harmonics will, their intermodulation products will introduce lot of other tones. Then this particular curve will give you the implications of that. I say that this is the output by input. What is that? My input, it is the power, so 20 log In in dB, and this is the output 20 log A out. If it is linear, that means it follows this alpha on xt. So, it will follow this straight line, but in spite of the defined, after a particular signal strength, input signal strength, the power level drops down. Why? Because now those nonlinear components will start to appear, and those will actually eat some of your energy. So, the voltage level of your fundamentals, this is at frequency omega and this is also at frequency omega, mind you. So, this drop in the gain, okay, that is called the gain compression. For any kind of amplifier design, LNA, this is a very important part, and when it is important, you should have a definition. What is that definitions? Now, what is the input level at which the gain is reduced by 1 dB? So, that is known as 1 dB compression points, right. So, now you can calculate pretty easily that what will, you know this expression, what is my omega constitution of this. So, you can find that this is the expression of omega t, you know, alpha 1 a 3 alpha 3 a cube by a 4. So, is a function of a cube, right. So, if you look at that, what is the 1 dB compression point, at that you can calculate this one, and then you can find out what is the 1 dB compression points. That means, what is the input signal power at which the gain of the amplifier will be reduced by 1 dB from its predicted gain if it is acted like a linear one is this, and then it is you can calculate from alpha 1 alpha 3, and that is a function of alpha 1 and alpha 3. Point is formula is pretty simple, but question is that it is only a function of the first order alpha 1 and alpha 3 is not depending upon alpha 2. It is does not depend upon the second order, but it depends on the first and the third, that means all odd orders. This gain compression depends upon that. So, for example, if you have say any signals, minus 37, 47 dB is a huge signal. For example, if you look at the minus 20 to 25 dBm, then it is 63 to 30.6, 35.6 millivolt peak to peak for a 50 ohm system. So, that is a huge power. Normally, you talk about 77, 80 dB kind of minus 77, minus 80 dBm power. Okay. So, if you look at the linearity of that, the linearity means 1 dB compression point is the maximum power is that. So, suppose you are say that is minus 10 dBm, it is the maximum power that can handle. If your signal strength is beyond that, definitely it will go to the nonlinear region, and that will introduce more number of harmonics in the systems, where the harmonics will cause lot of harm to your transceiver design, which I will come in the next part of the talk.